Now what we can do is combine these kinematic equations with splitting vectors into components to work out what happens with a projectile. So it actually turns out that projectiles follow parabolic paths. Let's have a look at a ball which is projected now.
So here it goes, and again in slow motion. Here you can clearly see that the path is shaped like a parabola.
So projectiles follow parabolic paths because we consider their horizontal and vertical motion separately. Vertically, the ball has gravity acting on it, so it's accelerating at a constant rate vertically. Horizontally, the ball travels with a constant velocity because there's no forces acting horizontally. In the next video, we're going to see the relationship between force and acceleration, which actually comes down about because of Newton's second law. So horizontally, it's going at a constant velocity, and vertically, it's accelerating. So it's very important whenever you're solving a projectile motion question to split the question into components. Consider what's happening horizontally separately to what's happening vertically. What's happening vertically will tell you about how high a projectile can go and how long it's in the air for, as it's when it hits the ground, which is a vertical displacement, that determines when the projectile motion is over. The horizontal motion will tell you about the range of the projectile or how far it has travelled. So let's do a couple of examples now of solving projectile type problems.
So the question is, an aeroplane delivers a care package. It drops this package when it is at a height of 950 meters above the ground. At this time, the airplane has a horizontal velocity of 105 meters per second and no vertical velocity. Part A. How long does it take the package to reach the ground? Part B. How far horizontally does the care package travel from when it was dropped to where it lands? Part C. What velocity does the package hit the ground with? Okay, so when we're starting a question like this, we should always draw a diagram. So here we've got our aeroplane. Here it is, here's the care package. It's 905 meters above the ground. And it's going at 105 meters per second horizontally. And this care package is going to keep traveling with a constant horizontal velocity and accelerate downwards. So it'll follow a parabolic path like that. So we know that the initial velocity in the x direction is equal to 105 meters per second. The initial velocity in the y direction is equal to 0 meters per second, as it has no vertical velocity. And we're asked how long does it take for the package to reach the ground. Well, that's going to depend on the vertical component because it's when y equals 0 that it hits the ground. And we know that it starts at a height, y naught, of, this shouldn't be 905, it should be 950. So this is 950 meters. So we're going to need to use our second kinematic equation, y is equal to y naught plus vy naught t plus a half ay t squared to work out the time it takes for the package to hit the ground. So we have that y is 0, it starts at a height of 950 meters. Vy naught is 0, it has no initial velocity, so that term is 0, we can ignore it, plus a half. Now the acceleration in the y direction is equal to minus 9.80 meters per second as it accelerates with little g towards the Earth. And that's times t squared. So we can rearrange this now to work out t squared. So we've got 4.90 t squared is equal to 950, and so that tells us that t squared dividing both sides by 4.9 is equal to 193.87, which tells us that t is equal to 13.9 seconds. So we've solved part A. Now part B, how far horizontally does the care package travel from when it was dropped to where it lands? So again, we can use this second kinematic equation, but in this case we need to work out its horizontal velocity, so we're going to have to use the horizontal version. So x is equal to x naught plus vx naught t plus a half ax t squared. Now we can call where it's dropped in the x direction 0, and this is x where it lands, what we want to find. So that term is 0. Vx naught, we're given up here, is 105, and the acceleration in the x direction, as long as we neglect air resistance, it's not accelerating in the x direction, so this is also 0, as this acceleration term is 0. So we've got, this is part B, x is equal to Vx naught, which is 105, times the time it takes to hit the ground, which is the 13.9 seconds. So solving that one on the calculator, we get 1,462 meters. So let's just give this to 3 significant figures, as everything else is to 3 significant figures. So this is 1,460 meters. And so sometimes this is referred to as the range. The range is the total distance traveled by the projectile. Now we're going to need a bit more space to calculate the final velocity. So let's clear some space. To calculate the final velocity, we're going to need to work out the final velocity in the x direction and the final velocity in the y direction. So let's work out Vx first. To work out Vx, we can use our first kinematic equation. Vx is equal to Vx naught plus ax t. And so there's no acceleration in the x direction. Vx naught, remember that was given to us, that was 105. So Vx is equal to 105 meters per second. So that tells us how fast it's going in the x direction. It's always going like this. Now what we're going to need to do is work out Vy. So Vy is equal to Vy naught plus Vayt. And so Vy naught was 0, Ay was minus 9.80, and the time it spent in the air was 13.9 seconds. So this will be equal to minus 136.22 meters per second. Meters per second, sorry, it's a velocity, not an acceleration. So this negative sign indicates that it's downwards. So Vy will be down like this. Vy is equal to 136.22. So now to get our total velocity, we need to add our x component, our horizontal component, and our y component, our vertical component. So we add them head to tail like this, and our resulting vector is this one here. So we'll represent its resultant with a double arrowhead here. So now what we need to do is work out what we can about this vector here. So first of all, let's work out its magnitude. We can use Pythagoras' theorem. The hypotenuse squared is equal to the sums of the squares of the other two sides. So v squared is equal to vx squared plus vy squared, which is equal to 105 squared plus 136.22 squared. And so v is equal to the square root of this, which is 172 meters per second. But now we've been asked to find a velocity, so we do actually need to give a direction as well. So we're going to need to work out this angle. So remember SOH, TOA. In this case, we know the adjacent side and the opposite side. So we're going to use tan. So we know that tan theta is equal to opposite over adjacent, which is equal to 136.22 over 105. And so solving this to get theta, we've got the inverse tan of 136.22 on 105, and this is equal to 52.4 degrees. So we can say that the velocity is 172 meters per second at an angle of 52.4 degrees below the horizontal. So now we've solved that problem. Now there's another problem for us to try. So the question, a golf ball is hit from the ground. It leaves the golf club with a speed of 15.0 meters per second at an angle of 45 degrees above the horizontal. Calculate the distance travelled by the golf ball. Okay, so to answer this question, we should always start by drawing a diagram. So here's our golf ball. It's going with an initial velocity v like this. This is an angle of 45 degrees, and this velocity is given by 15.0 meters per second. And we need to find out how far it's gone. A good place to start is to start by working out the initial vertical and horizontal components of the velocity. So we can split this velocity into a horizontal component here and a vertical component here. And to work out Vx, we have SOHCAHTOA, and Vx is the adjacent side, and we know the hypotenuse. So we can use cos of 45 is equal to Vx on 15, giving us that Vx is equal to 15 times cos 45. And so solving this, we end up with Vx is equal to 10.61 meters per second. Now for Vy is the opposite side, and we have the hypotenuse, so we use sine. So sine of 45 is equal to Vy over 15. So this tells us that Vy is equal to 15 times sine 45, which is equal to 10.61 meters per second. So now we have the initial, let's give these subscript naught for initial horizontal and vertical velocities. Now what we know is that the acceleration horizontally is 0. The acceleration vertically is equal to minus 9.80 meters per second. So we need to find out the total distance travelled by the golf ball. So that's a horizontal distance. Horizontally we've got x is equal to x naught plus vx naught t plus a half ax t squared. That's from our second kinematic equation. So we know that this acceleration is 0, so that term disappears, and we'll assume that it starts at the location 0, 0. So this x naught is also 0. So x is equal to vx naught t. We know what vx naught is, so we need to know what t is. Now the time of flight is going to depend on what's going on vertically, because it's when the vertical displacement is 0 again that it hits the ground. But to consider what's going on, let's break this flight into two parts. Let's consider how long it takes to get to its maximum height, and then again how long it takes to come back down to the earth. So what do we know about at maximum height? So at maximum height, we know that it has no vertical velocity. If it was moving up, then it would not be at its maximum height because it could go higher. If it was moving down, then it would not be at its maximum height because it would have been moving down for a small increment of time, so it would be slightly below its maximum height. So at maximum height, the vertical velocity is equal to 0. So we can use this to calculate the time it takes to maximum height. So time to maximum height. Now to calculate the time to maximum height, we're best off using our first kinematic equation. Vy is equal to Vy naught plus AYT. So Vy, that's 0. Vy0, we've calculated that as 10.61. AY is accelerating downwards, so minus 9.80 times t. So we've got 9.80 t is equal to 10.61, and so t is equal to 10.61 divided by 9.8, which is 1.08 seconds. So we know how long it takes now to get to maximum height. Now actually, because of symmetry, it turns out that it takes the same time to get back to the ground as well. But I won't expect you to take my word for that. Let's go ahead and show it. So to work out how long it takes to get from this maximum height back to the ground, we're going to need to know what this maximum height is. So let's now find maximum height. We've got y is equal to y0 plus Vy0t plus a half AYT squared, and y0's 0. Vy0 is 10.61, so we've got 10.61 times the time, 1.08, plus a half times minus 9.80 times 1.08 squared. And so we can type all this into the calculator and we get 5.77 meters. So this maximum height here is 5.77 meters. So now we can work out how long does it take to fall from rest here back to the ground, which is 5.77 meters away. So to do that, we'll need to use this second kinematic equation again. So we've got y ends up at 0. It starts at 5.77. Now, the initial velocity from this point is 0. It's at rest vertically there, because that was what's decided that it was at its maximum height. And then we've got a half, AY is minus 9.8 t squared. So we've got t squared is equal to 5.77 over 4.9, and so solving this on the calculator, we end up with t is equal to 1.08 seconds, which is the same as the time it took to get to that maximum height. So now we know total time is equal to 1.08 plus 1.08. That's the time to maximum height plus the time to return to the ground, which is equal to 2.16 seconds. So now what we can do is go back to this equation we had at the beginning and substitute in. And so x is equal to Vx0, which is the 10.61 times 2.16. And solving that on the calculator, we get 22.9 meters. So the range of this projectile, the total distance it's traveled, is given by 22.9 meters.